Hello and welcome to lecture 9 of the course Computational Complexity. So before I begin, I thought I will just share a couple of small pointers. One is that for all the material that I have been covering so far, the textbook is The Introduction to Theory of Computation by Michael Sipser. Right, so this is for whatever I have been doing so far. Later we will change books because we will choose some other books for the content required from there, and whichever book it is, I will share the reference, right? And communication channel for this course, I realized that there is NPTEL provides a Google Groups, so you could ask questions through that when you log in and view the video from the NPTEL portal, not necessarily from YouTube. There is the Google Groups provided by NPTEL, and we will also provide a Discord server where we will be able to have more flexibilities like we'll be able to classify questions into different topics, let's say week wise, something like that. So I will share the details of these by email. There will be so some of you have been emailing and asking, will there be live sessions? There will be live sessions. I don't know the exact mode, that will be decided by NPTEL. Another thing is that whatever notes I am writing down, I will share all of this. Okay, so till now I have not figured out how to do that, but I will get in touch with the NPTEL folks and then share it. Another point about the pace of the course, please let me know about the pace of the course via YouTube comments or via Google Groups or whichever way you can, because I'm going a bit slow as per what I had originally planned, but I think this may suit the class better. That is the reason for going a bit slow. If you feel it is too slow, please let me know. I could go a bit faster. In any case, we will soon pick up a bit of pace after the first couple of weeks. Okay, so with that, today's topic is NP-complete problems. So we have already seen SAT, 3-SAT, etc. Now today we will see other NP-complete problems. So let us see. So we saw CLIQUE. What was CLIQUE? CLIQUE was this language, right? You were given graph G and a number K. G is an undirected graph. With a K-clique, right? So a clique is a set of vertices such that each pair of vertices are adjacent to each other. So for instance, in this figure, right over here, these three vertices form a clique, right? Because these three vertices form a clique because they are all adjacent to each other. And in this graph, there is no 4 clique. There is only a 3 clique. There is no 4 clique because you can see that there is no 4 clique, right? So if you try to include this, but then this vertex and this vertex, the one on the top, they are not adjacent to each other. Okay. So in this case, so this is this I am claiming is an NP-complete problem. We have already seen almost all the ingredients for the proof that it is NP-complete. One is that clique is an NP. Why is this true? Because given an instance G and a number K, you could simply guess K vertices, right? Non-deterministically choose K vertices and then have a polynomial time verifier. So if I give you K vertices, one should easily be able to verify that this is a K clique or not, right? So again, by the verifier characterization of NP, we could verify that clique is an NP. The next is that the NP hardness, that is all the languages in NP are reducible to clique, right? So we need to show that for all A in NP, A reduces to clique. However, in an earlier lecture, I think lecture 5, maybe, yeah, lecture 5, I think we saw that 3 sat reduced to clique. We saw the polynomial time reduction from 3 sat to clique. So we will use that to show this. So we already know that for all A in NP, A reduces to 3 sat, right? And then we know that 3 sat reduces to clique in polynomial time. And I have not proved this in class, but it should be possible for you to calculate and verify that these two together, A reduces to 3 sat and 3 sat reduces to clique, these two together imply that A reduces to clique. That means for all the languages A in NP, A reduces to clique. So this is again one interesting thing that we will do. So we proved that SAT is NP complete from scratch, right? We had this whole Cook-Levin setup, computational tables, and showed that any language in NP reduces to SAT. Now we are not going to be doing that kind of setup from now on. To show that a language is NP complete, all we will do is we will have to do is that one is that the language is in NP, like here clique is an NP, and two is that we will reduce some NP complete language to it. So here we reduce 3 sat to clique, right? Not here, but in lecture 5 we reduce that. So instead of 3 sat, we could do this with any other NP complete language, right? So in this case, 3 sat is the one of the languages that we know is NP complete, so we use 3 sat. But now that we have established that clique is NP complete, now next time I could reduce clique to some other language to show that that language is NP complete, right? So we could build up a set of NP complete languages and then reduce from any one of them to show that that language is NP complete, right? So now let me introduce another problem called Vertex-Cover, right? What is a Vertex-Cover? So first I'll tell you what is a Vertex-Cover, right? A Vertex-Cover, so given an undirected graph, right, VE, Vertex-Cover is a subset of vertices such that all the edges are covered by these vertices. So let us see. So here, so consider this graph in the right side. Now let's say I cover this. So now which are the edges, vertices that are not covered? So this edge is not covered, right? So I will include this. And now if you take any edge, one of its endpoints, at least one of its endpoints is there in the green or blue set. So there is it is there as a circled vertex. So these 6 vertices form a vertex cover. If you take any vertex, sorry, if you take any edge, one of its endpoints is a circle vertex, right? So now, so there is a vertex cover with 6 vertices. Is there a one with a smaller? Is there a smaller vertex cover? Yes, you may have noticed that the stop vertex is not really essential, right? Because this covers these 2 edges, which are anyway both already covered, right? So we could skip that. So now this is a vertex cover with 5 vertices. Now, is this 5 necessary? Good question, because so we have 1, 2, 3, 4, 5, 6, 7. There is a cycle of 7 cycle outside, and so perhaps I could remove this bottom vertex. I could include this. Right, but it's still 5 vertices, right? So now if I remove the middle vertex, then this edge becomes uncovered, right? So it looks like you need at least 5 vertices to cover this. You could verify whether it is 5 or can we do it with 4. So this is a vertex cover, and the language vertex cover is given a graph G and a number K. Is there a vertex cover with only K vertices or with K vertices, right? So we are with vertex cover, we want to see what is the smallest possible size. right? Right. So let's see another example. So this one, for instance, maybe I need to include the same. So one strategy would be to, again, this is just, these are NP complete languages. We'll soon see it's NP complete. So the heuristics, and we don't expect to be there to be a simple solution, right? So one heuristic would be to pick all the high degree vertices. So let's say this, and let's say, and there is a 1 2 3 4 5 6, there is a 6 vertex cycle. So just to cover these outside 6 cycle, we need to take something like this. At least 3 vertices need to be there, right? And this one needs to be there, and this one needs to be there. I think we are done. So again, 6 vertices are required. I'm not sure if it could be done by a smaller set. Maybe, but not sure. Okay. So again, vertex cover is given a graph G and a number K. Does there exist a K sized vertex cover for this graph? This is NP complete also. The first part is easy. The membership of vertex cover in NP, this is easy. Just like I argued for CLIQUE, given a vertex cover, it's easy to verify. You can just run through all the list of edges and see if each and every edge is covered. The second point, the NP hardness, are all the languages in NP reducible to this? We can do that by reducing 3SAT to vertex cover, right? 3SAT to vertex cover, because 3SAT is an NP complete language, a known NP complete language, we could reduce that to vertex cover. So this is there in the book, meaning Sipser, right? This is there in Michael Sipser's book. You could have a look at that, but there is also a simpler reduction, right? I find it simpler. What you could do is to, you have already seen CLIQUE is NP complete, right? So you could, so instead of 3SAT, we could reduce CLIQUE to vertex cover. So you could reduce CLIQUE to independent set. Okay. Independent set is a set of vertices such that no two vertices are adjacent. So it's a kind of the opposite of CLIQUE. CLIQUE is a set of vertices, so that any two vertices you take, they are adjacent. Independent set, any two vertices you take, they don't have an edge between them, right? And then you can show that independent set in turn reduces to vertex cover. So this is not really that hard. You can think about it. So if some vertices form a vertex cover, what do the remaining vertices do, right? If the remaining vertices, what can we say about them? Can they have an edge between them? This is something that you can think about. Okay, so this you can think about, right? It's not that difficult. Even this you should think about. Okay. For the rest of this lecture, I will give a very brief, not brief, maybe high level picture of the yet another NP complete language called Hamiltonian Path. Okay. Again, the idea is like these proofs can be a bit long, but I do not want to go through these proofs because these proofs are like I want to get to other things, not just stick with NP completeness. 2, they are available, and 3, I want to just give a high level idea that rather than go to the details of these proofs, like at least the NP completeness proofs. So if you have questions, you could ask me via email, or I prefer the forum, because if you ask via the forum or Discord or whatever, then whatever question you ask will also be visible to everyone else. So and there will be a better engagement. So maybe what you are asking is possibly what many other students wanted to ask, right? So I prefer if all the questions are asked through the forum or the Discord, which I will details of which I will share with you, right? Okay, so what is Hamiltonian path? So I'll explain for a directed graph. So there is also an undirected variant, which is exactly what you would imagine it to be. I'll state the problem for the directed graph setting, right? So what's a directed graph? It's a set of vertices and edges, and the edges are directed, right? So there is each edge has a direction. So here there is an edge from S to B, right? I'm referring to the picture on the right side. There is an edge from S to C. There is no edge from S to D. However, there is an edge from D to S. There is an edge from B to S also. So S to B and B to S, B to C, C to D, C to E, E to T, and D to T, right? The question is this. So I designate two vertices S and T. Is there a path? So the question is there a path that starts from S, ends in T, and goes through all the other vertices exactly once, right? So let's see in this case, right? So you can go from S to B, then B to C, then C to D, D to T, but then you are stuck because there is no other way from T, right? So can you do something else? Let's say you start from S to C, but once you go from S to C, there is no other there is no way you can cover B. The only way to reach B is to go back to S again, which is not allowed. So you have to start from S to B, B to C, then C to E if you try, and then E to T if you try. Then from T you cannot go back because the T is like a sink. Sink means there is only incoming arrows to T, right? So again it's bad. So none of these work. However, if you had an edge, let's say S, B, C, D, T, if you had which edge would make it a have a Hamiltonian path? So one would be S, B, C, E. So if there is an edge from, let's say, E to D, right? So then you could have the following Hamiltonian path, right? You could go from S to B, B to C. Maybe I'll write down S to B, B to C, C to E, E to D, and D to T. This is a Hamiltonian path, right? So, but in the original graph, this edge ED was not there, and hence the original graph did not have a Hamiltonian path. So again, formally, Hamiltonian path, written Ham path, is a directed graph and two designated vertices S and T, such that there is a Hamiltonian path from S to T, meaning there is a path from S to T that goes through all the other vertices exactly once. So now we will show that it is NP-complete, or rather I will show the high level idea of why it is NP-complete. First part is easy, to show that it is indeed in NP, right? Again, you can use the verifier characterization. You can guess all the other vertices. So you know it starts in S, it ends in T, and you basically, there are n-2 other vertices in the graph, and you guess all the other n-2 vertices in some order, and then so once you guess it, and then you just go from S to V1 to V2 to V3 up to Vn-2 and then to T, right? You try to go that way. Now, is that a valid Hamiltonian path? Is what one has to guess, or what one has to verify. Perhaps there is an edge from S to V1, edge from V1 to V2, but there is no edge from V2 to V3. This would mean that that is not a Hamiltonian path. But an actual Hamiltonian path will have all the vertices arranged in the correct order, right? And all of them are distinct. And these things can be verified, right? So I am not going into the details, but this should be easy for you to verify. Again, this is something that you can think, right? The next thing is to show that all the languages in NP reduce to Hamiltonian path in polynomial time. Again, like I showed earlier, we could reduce one of the known NP-complete languages to Hamiltonian path. The NP-complete language that we pick is 3SAT, right? So this part is where I will briefly explain in the high level and not go into the detail. So given a 3-sat instance, we will construct a Hamiltonian path instance such that the 3-sat instance is satisfiable if and only if the Hamiltonian path instance is a S instance, meaning the graph G has a ST Hamiltonian path, right? So again, what do we need to argue? We need to argue that this construction is in polynomial time. Given phi, which is a 3-sat instance, the construction of the Hamiltonian path instance GST, this construction is in polynomial time. This is not that difficult to see. And then we have to show this kind of equivalence condition, right? The condition being, maybe we'll just erase this. The condition being, the phi is a S instance of 3-sat if and only if GST is an S instance of Hamiltonian path. Meaning phi is satisfiable if and only if G contains an ST Hamiltonian path, right? If one of them is a yes instance, the other should be yes. If one of them is a no instance, the other should be no, right? So consider, so we are given with a 3-sat instance phi with m clauses and n variables, say, okay, m clauses and n variables, clause 1, clause 2 up to clause m, okay, and the variables, let it be x1, x2 up to xn, right? So maybe the variables are x1, x2 up to xn, okay. So which means each of these a1, a2, a3, a2, b1, b2, all of them are either some xj or some xj complement, right? These are the literals, right? So now how can we use this to construct a graph? So think about it. We are given a Boolean formula and now we have to construct a graph, right? So this Boolean formula is something like variables, yes, no, true, false, etc. And the graph, we want to check whether there is a path from one vertex to another vertex. So at least on the surface of it, it seems very, very implausible, right? So because one is entirely different from the other. But let's see how one could use gadgets in a creative manner, right? So what we have is a very somewhat elaborate construction, right? So we will have this graph that contains many vertices. So this is the construction. So we have n variables, right? So you have these diamonds. So you see the first diamond. I'll just circle it for now, which I will. So this is diamond number 1. This corresponds to x1. And then you have diamond number 2 corresponds to x2, and so on up to n diamonds. The final one corresponds to sxn. And all the arrows, if you see, all the arrows are going downwards from S, these two sides, and from these two sides to the next vertex over here, and again down, 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 etc. And then there is a chain of vertices in the middle, right? I have written here 3m plus 3 nodes. There is a chain of vertices in the middle such that there is arrows both ways, from right to left and from left to right, right? And the number of vertices including the extreme vertices are 3m plus 3, right? So, and like that I have constructions here also 3m plus 3, right? So starting from here till here, and same here 3m plus 3. And within this there are some categorizations. This green box is for the clause C1, right? And the next, after one vertex, the next boxes will be for clause C2 and so on, right? I don't want to get into this detail now because that is required for the full proof, but I just want to give you a high level idea, right? So the thing is this. So now let's leave, there are some, you see there are some vertices in the side C1, C2, C3 up to Cm, right? This ones. I don't want to get into these side vertices for now, but ignoring these side vertices, how many ways are there to go from S to the S, which is the top vertex, to T, which is the bottom vertex, right? So let us ignore these side vertices now. So you could start from S, go to the left side, then come down. But once you come down, these middle vertices are not covered. So you can start from S, go to the left side, then use the middle vertices and travel to the right side, and then come down, right? And once you come down, you do the same for the next one. So there are two ways to traverse this diamond. The top diamond, you can start from S, you could go to the, you could do something like this, which is what I will call zigzag, or you could do something like this, which is what I would call zag-zig, right? So basically each diamond has, you could go from the top left, move to the right and then down, or top right, move to the left and then down, right? So this is zigzag and zag-zig, and we can do this in each of these diamonds. So you could zigzag or zag-zig on the top diamond or the second diamond and so on. So there are two choices for each of these diamonds. So that is 2 power n choices in all, right? So again I have written that below. At each diamond we could zigzag or zag-zig. That means we have 2 power n choices. And the clause vertices will come into play. So right now you will see that whatever I have described just depends on the number n, which is the number of variables, and number m because the middle one has 3m plus 3 nodes. Again you can calculate the total number of vertices, which will be 3m plus 3. I can calculate 3m plus 3 into n, right? There are n diamonds, and then there are n plus 1 starting from S and going down to T, right? And then there are these m clause vertices. So the construction is simple, but right now the actual formula itself has not really come into play except the number of variables and the number of clauses. So that will the exact formula will determine how we interconnect these diamonds with the side vertices, the right side vertices. Again, this is also there in the book. I will not get into the details, but the idea is this: there are 2 power n choices for one to traverse from S to the bottom vertex T, but then the graph also involves the side vertices, right? If the formula has a satisfying assignment, there will be a way to include all the side vertices, and if the formula does not have a satisfying assignment, we will not be able to include the side vertices whatever we try. This is the cleverness of the construction. And how does it happen? That is because notice that at each diamond we can make one of two things: go zigzag or zag-zig. So this corresponds to setting that variable as true versus setting that variable as false. So 2 power n ways to traverse from S to T is exactly corresponding to 2 power n ways to set x1, x2 up to xn different assignments, right? So that's that many different assignments, right? And so that way, and all these vertices will be covered except for the clause vertices, this side vertices. And what I am saying is that these side vertices also can be covered if and only if there is a satisfying assignment. If there is no satisfying assignment, you will not be able to cover all the side vertices. Again, the details are there in the book. It's also there in the notes that I have prepared, and I shall share this with you, right? So again, the details are a bit involved. If there is, so the first part is that if there is a satisfying assignment, then there is a way to traverse all the vertices, including the side vertices, clause vertices. And if there is no satisfying assignment for the clause, for the formula, then no matter what you try, you cannot do this. In fact, what we will do is do the contrapositive. If there is a Hamiltonian path, we will show that there has to be satisfying assignment, right? Right. Now I'll just complete the lecture by saying two small things. Now that we have shown Hamiltonian path is NP-complete, which is the directed Hamiltonian path. Now, can you use that to show that undirected Hamiltonian path is NP-complete? So, what would be undirected Hamiltonian path? It will be the same as directed Hamiltonian path, but just that the graph is undirected. G is an undirected graph that has a Hamiltonian path from S to T. This is not that difficult. There is a reduction from Hamiltonian path. And Hamiltonian cycle, G, it's just a graph. So I'll just, there is no S and T. It's a directed graph. Directed graph that has a Hamiltonian cycle. What is Hamiltonian cycle? Hamiltonian cycle is a cycle that goes through all the vertices exactly once. All the vertices exactly once. So there is no ST designation. So let's say suppose this is G, right? This is S and this is T, right? Suppose G has a Hamiltonian path. Now I am making a new graph. Let me call it G dash. G dash is all the vertices and edges of G plus another edge that is a directed edge from T to S. Okay. All the edges and vertices of G plus another edge from T to S. So now if G has a Hamiltonian path, right, something that goes through all the vertices from S to T, then you could combine that path with the TS directed edge to form a Hamiltonian cycle. So if G has an ST Hamiltonian path, you could combine that with the TS edge to form a Hamiltonian cycle. But so if G has a Hamiltonian path, if and only if G prime has a Hamiltonian cycle. Sorry, so what we have is G has a Hamiltonian path implies G prime has a Hamiltonian cycle. So I should say ST Hamiltonian path. Okay. Implies G prime has a Hamiltonian cycle. But can we say the opposite? Can we say the reverse direction? Not necessarily, right? If G prime has a Hamiltonian cycle, we cannot insist that G has a Hamiltonian path, because that cycle need not make use of the edge from S to T. So can you do something to make sure that this edge from S to T is used or T to S is used, right? Because if there is a Hamiltonian cycle within this, without using this edge, TS edge, let's say this itself has a Hamiltonian cycle, G itself has a Hamiltonian cycle. Now that doesn't mean that G has an ST Hamiltonian path. There could be some other Hamiltonian path. That need not mean that G has an ST Hamiltonian path, because we are not, if there is a Hamiltonian cycle that uses the TS edge, we could just drop that edge and get an ST Hamiltonian path, but that need not be the case. So how do you modify the construction so that instead of this edge from TS, can we do something else? This is something that you can think about, right? And that's about it. That's about this. So we saw some more NP-complete languages. CLIQUE, we saw that it's NP-complete. Vertex-Cover, I also mentioned independent set and Hamiltonian path, and at the end undirected Hamiltonian path and Hamiltonian cycle. I didn't go through the proof of any of this in detail, but I hope I've given you enough food for thought. Please ask questions, please engage the forums and the Google groups or the Discord. I'll share very soon the channels with you.